The distances that separate objects in space exceed anything the human mind can truly comprehend. Our brains, shaped for earthly scales, struggle to grasp the frozen immensity of cosmic abysses. And yet, thanks to scientific instruments, we have acquired an extraordinary ability, the power to look across thousands, millions, sometimes billions of light years, and to extract knowledge from them. Every captured photon tells an ancient story, carried to us from the depths of time. By combining the rigor of science with the power of imagination, we can embark on an extraordinary journey, a voyage that will take us across the entire universe. Our trajectory will begin with a dizzying leap into the past, to a time when our planet was still a hostile world, long before the rise of the dinosaurs. By tracing the evolution of life over hundreds of millions of years, we will witness global catastrophes, mass extinctions, and perhaps even upheavals similar to those the Earth is experiencing today. Then, leaving our home planet behind, we will extend our gaze beyond Earth through the James Webb Space Telescope, surveying space with unprecedented precision. We will explore distant objects, strange worlds, and pause on two fascinating planets where life could, hypothetically, exist. Another detour will lead us to a cosmic giant, Stephenson 18, one of the largest stars ever observed in our galaxy. The journey back will be long enough to give us time to reflect on a fundamental question. Where is the center of the universe, and does it even exist? Does this hypothetical place conceal something mysterious, unknown, or unimaginable? The answers to these questions lie somewhere, buried deep within the silent depths of space. It is time to set out in search of them. For most of its history, Earth was anything but a welcoming refuge. To understand what it truly was, we must travel back to the Archean, the oldest eon marked by the emergence of life. This period began around 4 billion years ago and lasted for nearly 1.5 billion years. The young Earth had only just survived a second massive bombardment. Thousands of tons of rocky debris, remnants of the formation of the solar system, were still crashing into its surface. These violent impacts shattered the thin, barely solidified basaltic crust, exposing an ocean of incandescent magma. Yet despite this chaos, the planet continued its slow cooling. Gradually, a primitive lithosphere formed, covering the molten layers beneath. It took nearly another 1 billion years before the first living organisms emerged. At that time, Earth's surface was surprisingly uniform. Tectonic plates, whose collisions could have given rise to towering mountain ranges, had not yet had time to become fully active. Geological diversity was extremely limited. Mineral deposits and rock strata were only just beginning to form. Earth's crust was dominated by basalt, an igneous rock produced by the solidification of lava. The Archean atmosphere contained barely any oxygen, and nitrogen levels were far lower than those we know today. The planet was enveloped in a thick, dense mantle of water vapor and carbon dioxide, enriched with sulfur oxides, phosphorus, and other highly reactive chemical elements. At that remote time, the sun shone less intensely. According to some estimates, its luminosity reached only about 70% of its current value, plunging Earth into a state of perpetual semi-darkness. The Moon, still very close, exerted a considerable influence. Days lasted only about 10 hours, and tides sometimes rose tens or even hundreds of meters high. As the planet cooled, atmospheric water vapor condensed, triggering torrential rains. These downpours first formed vast expanses of shallow water across the lowlands. This primordial water was acidic, highly saline, and extremely hot, at times close to boiling. Its composition resembled that of modern geysers. Paradoxically, this environment, one we would today consider uninhabitable, became the cradle of life. The earliest organisms were anaerobic. Free oxygen, essential for our respiration, was absent. To survive, these primitive life forms relied on alternative chemical reactions to produce energy. Archean microorganisms could not swim and depended on solid surfaces on which to grow. The biosphere was then limited to a thin, viscous film, only fractions of a millimeter thick, coating the coastal zones of a warm, shallow ocean. This living layer did not extend beyond roughly 20 meters below the surface. The dense atmosphere blocked most solar radiation, preventing light from penetrating deeper. In the abyssal depths, near submarine volcanic vents, chemosynthetic bacteria thrived. They had no need for light. The energy they used came from chemical reactions involving sulfur and iron. Meanwhile, the planet continued its slow transformation. Ocean levels rose, the atmosphere gradually thinned, and the sun steadily grew brighter. The life-friendly coastal band slowly expanded. By the end of the Archean, the biosphere appeared as a narrow fringe along the continents, accompanied by a few isolated pockets of life around underwater volcanoes. Dry land, rivers, and most of the open ocean remained completely sterile. Had an observer walked the Earth at that time, stromatolites would have been the only visible evidence of life. These limestone structures, sometimes several meters tall, resulted from the activity of ancient microorganisms. Another major obstacle to the development of life was the scarcity of recycled elements. Scavengers did not yet exist. Dead organisms accumulated in oceanic depressions, and hundreds of millions of years later, these deposits would give rise to oil reserves. Then, around 3.5 billion years ago, organisms appeared that would radically transform the planet. Some bacteria mastered a revolutionary process: oxygen-releasing photosynthesis. A billion years later, at the boundary between the Archean and the Proterozoic, this innovation triggered the greatest biological catastrophe ever known. Today, it is called the Great Oxidation. Its exact magnitude remains difficult to assess, as nearly all organisms of the time left no fossil record. Most anaerobic life, shaped by a billion years of evolution, was annihilated. Methane, a powerful greenhouse gas, reacted with oxygen to form carbon dioxide and water. The rapid drop in its concentration caused a sudden cooling of the planet. Thus began the Huronian glaciation, the most extensive ice age in Earth's history. It started around 2.4 billion years ago and lasted nearly 300 million years. Glaciers sometimes reach the equator, transforming Earth into a true snowball world. In the span of 1.5 billion years, our planet had shifted from a boiling volcanic hell to an endless frozen desert. The Proterozoic period spanned an immense length of time, from around 2.5 billion years ago to approximately 540 million years before the present era. Despite the extreme cold caused by major glaciations, life did not disappear. It persisted, discrete and fragile, in limited refuges, mainly along coastal regions near the equator. Dry land, however, remained completely sterile for much of this period. No plants or animals yet walked the continents. And yet, in the absence of life, major transformations were slowly reshaping the planet's surface. The continents began to emerge more clearly. Metallic deposits formed deep within the crust. New layers of rock accumulated over time, permanently altering the face of the globe. Depending on the era, Earth alternated between landscapes of endless glaciers and wind-scoured rocky deserts. It is difficult to imagine that just 500 million years ago, much of Earth's surface looked more like the Martian desert than the lush planet we know today. But gradually, the sun grew brighter and warmer. The ice retreated, slowly freeing entire regions. Around 542 million years ago, the Phanerozoic began, literally the era of visible life. It was a time marked by both spectacular explosions of biodiversity and devastating mass extinctions. Life, now complex, finally left abundant fossil traces. At the beginning of the Paleozoic, much of the emerged landmass merged to form a colossal supercontinent, Gondwana. Located mainly in the southern hemisphere, it featured rugged terrain and covered more than 100 million square kilometers. It comprised what would later become Africa, South America, Antarctica, Australia, the Indian subcontinent, and several other regions. Farther north, smaller continental masses, Laurentia, Baltica, and Siberia, occupied equatorial latitudes. Numerous islands were scattered around them. Despite this complex geography, dry land remained almost entirely devoid of life until the beginning of the Silurian, around 444 million years ago. Only a few primitive mosses and rudimentary lichens slowly began to colonize exposed surfaces. It was not until the very start of the Silurian, in tidal zones and along riverbanks, that the first true plants appeared. Even then, their presence was limited to tropical regions. In the oceans, the situation was different. Marine life diversity increased rapidly, though it remained concentrated near coastlines. The habitable zone gradually expanded. During the Devonian, which began around 420 million years ago and ended near 358 million years before the present era, The maximum depth accessible to photosynthesis reached about 50 meters, 10 times less than today. It was during this time that the first decomposers appeared. These organisms, capable of breaking down dead organic matter, profoundly altered ecosystems. Thanks to them, life extended to depths approaching 500 meters, where not only scavenging bacteria were found, but also marine sponges. Then came the Carboniferous, a period stretching from 358 to 299 million years ago. In tropical regions, immense tree ferns formed dense yet fragmented forests. At that time, organisms had not yet evolved the ability to efficiently decompose wood. Once dead, the giant trunks did not rot. They accumulated on the forest floor, preventing the release of phosphorus essential for plant growth. Over time, these plant masses were transformed into vast coal deposits, still exploited today by human industry. Outside the tropics, only fungi, mosses, and lichens survived. Their shallow root systems failed to stabilize the soil. Rainfall caused intense erosion, turning rivers into muddy torrents and plains into stagnant marshes. Vast arid regions became true biological deserts. In the seas and rivers, fish experienced rapid diversification, yet life remained confined to coastal zones. Algae had not yet developed the ability to float freely, preventing the colonization of the open ocean. Animals still depended on shorelines. The Carboniferous then gave way to the Permian, which began around 299 million years ago and ended near 252 million years before the present era. The first amphibians ventured onto land, and plants began spreading towards subtropical regions. Marine life remained concentrated in shallow waters. The end of the Permian was marked by the greatest mass extinction in the entire history of multicellular life. According to some estimates, up to 96% of marine species and 73% of terrestrial species vanished. The exact causes of this catastrophe remain uncertain. However, the following period, the Triassic, which inaugurated the Mesozoic era, quickly compensated for these losses. Life reached a new level of complexity. For the first time, forests expanded into temperate latitudes. The oceans underwent a major transformation. Blue-green algae, similar to those we know today, appeared. They no longer needed to anchor themselves to a substrate. Photosynthetic microorganisms colonized the upper layer of the global ocean. They were followed by fish, mollusks, and arthropods. Organic debris sinking into the depths nourished an abundant benthic fauna. The ocean gradually took on a modern appearance. The Mesozoic era, spanning from 250 to 66 million years ago, comprised three major periods: the Triassic, the Jurassic, and the Cretaceous. This era is inseparable from the image of dinosaurs. Cinema and popular science have largely shaped our perception of these ancient creatures. But contrary to popular representations, Earth was not covered in dense tropical forests from pole to equator. If forests reached high latitudes, it was due to globally warmer temperatures than today. Equatorial regions, by contrast, often became arid. Despite the widespread presence of forests, vast areas remained marshy or desert-like, sometimes cool, sometimes humid, but poor in herbaceous vegetation. It was not until the middle of the Cretaceous, around 100 million years ago, that angiosperms began to spread. Initially appearing as trees, herbaceous plants emerged later. They profoundly transformed landscapes. Their dense root networks strengthened soils, reduced erosion, and regulated moisture. Deserts turned into steppes and savannas, marshes into floodplain meadows, and frozen zones into tundras. By the end of the Cretaceous, Earth already closely resembled the planet we know today. Only one final key element was missing: the dominance of mammals. The end of the Cretaceous marked a decisive turning point in the history of life on Earth. Mammals had existed for a long time already. Discrete, nocturnal, and often small in size. They lived in the shadow of the dinosaurs, occupying marginal ecological niches. But everything was about to change. To this day, the exact causes of the dinosaurs' extinction remain debated. The impact of a gigantic celestial body, a global climatic cooling, extreme volcanic activity, or a combination of these factors are often cited. Whatever the reasons, the outcome was unmistakable. The giant reptiles vanished, freeing vast spaces within terrestrial and marine ecosystems. Over the next 66 million years, mammals underwent a spectacular diversification. From small marsupial-like creatures, they evolved into remarkably varied forms. Majestic whales roamed the oceans. Formidable felines dominated the land. Sturdy camels adapted to arid environments, while agile bats conquered the night sky. At the end of this long evolutionary process, a singular species emerged, a living being that did not merely adapt to nature, but actively transformed it. A species capable of extracting coal formed from forests that had vanished hundreds of millions of years earlier in order to keep warm. A species capable of altering landscapes on a planetary scale. That species is Homo sapiens. Development of life on Earth has never followed a linear path. It has been punctuated by periods of explosive expansion and near-total crises. These conclusions are based on the analysis of fossilized sedimentary layers studied through paleontological excavations. Over the last 540 million years, scientists have identified at least 5 major mass extinctions and around 20 less significant events. Yet the most severe crisis in Earth's biosphere occurred long before that. Around 2.1 billion years ago, during a fundamental upheaval in planetary chemistry. The earliest forms of life are thought to have appeared nearly 4 billion years ago, only a few hundred million years after Earth's surface became relatively stable. At that time, Earth presented a bleak spectacle. Bare, rocky expanses, skies heavy with thick clouds, violent storms, frequent earthquakes. The atmosphere was devoid of oxygen and composed mainly of nitrogen, methane, and carbon dioxide. The planet was then dominated by primitive microorganisms, archaea, and bacteria. Most of them practiced a form of photosynthesis that did not release oxygen. There also existed many intermediate forms, positioned at the boundary between the living and the non-living. Around 2.7 billion years ago, a major biological innovation appeared. Oxygenic photosynthesis, the process we know today, made it possible to release oxygen into the environment. This mechanism is still used by many plants and unicellular algae. For anaerobic organisms, oxygen was a deadly poison. The new oxygen-producing life forms gradually eliminated their competitors, occupying the ecological niches left behind. At first, oxygen reacted with the surrounding rocks. Localized pockets of oxidation formed. Gradually, oxygen accumulated in the atmosphere. It oxidized methane, sulfur compounds, and iron-rich minerals. Organisms unable to survive in an oxygen-rich environment nearly disappeared, persisting only in isolated underground refuges. The biosphere seemed to have inverted. Oxygen-producing organisms now dominated the planet. The former inhabitants, once thriving, were confined to marginal zones. This chemical transformation caused a significant reduction in greenhouse gases. Methane was converted into carbon dioxide and water. Carbon dioxide, in turn, was absorbed by photosynthetic organisms. The greenhouse effect weakened abruptly. Earth's surface temperature fell. The Huronian glaciation began around 2.1 billion years ago and lasted nearly 300 million years. It was a period of extremely slow evolution, marked by repeated episodes of global glaciation. All of these upheavals are now grouped under the term Great Oxidation Event. This process was neither rapid nor uniform, but it was total. Almost all of the biological diversity developed during the oxygen-free era disappeared. Evolution entered a phase of stagnation that lasted nearly 1 billion years. All of this occurred to allow life to adopt a more energetically efficient mode of functioning. Around 540 million years ago, the Phanerozoic era began. Visible life exploded into a multitude of complex forms. Many of these ancient creatures now seem as though they came from a fantastical world with no modern equivalent. But this expansion was brutally interrupted. Around 450 million years ago, an unknown event triggered the Ordovician-Silurian extinction. Among the hypotheses are a cosmic gamma-ray burst, intense volcanic activity, or the impact of a massive celestial body. Between 25 and 50% of all living beings disappeared in less than 7 million years. Trilobites, mollusks, and many marine invertebrates were particularly affected. The late Paleozoic then witnessed a renewed expansion of terrestrial life. Vegetation colonized the continents. The first amphibians and reptiles appeared. Fish became dominant in both freshwater and marine environments. Around 372 million years ago, the Devonian extinction began. It occurred in several waves, separated by brief periods of relative stability. Even during these lulls, extinction rates remained high. Land plants had developed deep root systems. Erosion carried large quantities of nutrients into the oceans. Under these favorable conditions, algae proliferated. Their decomposition consumed dissolved oxygen, suffocating marine life. Nearly 70% of marine species vanished, including almost all reef-building organisms. The oceanic biosphere was profoundly transformed. After the upheavals of the Devonian, Earth entered a phase of profound transformation. The Carboniferous spanned nearly 60 million years, from 359 to 299 million years before the present era. At that time, the configuration of the continents and the composition of the atmosphere favored the expansion of vast tropical forests. Oxygen levels reached exceptionally high concentrations, at times exceeding 30% of the atmosphere. This abundance of oxygen allowed the emergence of life forms of spectacular size. Giant insects roamed the forest undergrowth. Arthropods reached dimensions unimaginable today. Yet this abundance concealed a fragility. Organisms capable of decomposing lignin, the primary component of wood, did not yet exist. Dead trunks accumulated, were buried, and slowly transformed into coal. Essential nutrients trapped within this biomass became inaccessible to living plants. Vegetation remained dense but unstable. Soils, poorly structured, were easily eroded by rainfall. Rivers frequently changed course. Landscapes alternated between lush swamps and arid zones. By the end of the Carboniferous, climatic conditions began to deteriorate. Glaciers advanced once again. Sea levels fell, fragmenting coastal habitats. These changes heralded the transition into the Permian. The Permian began around 299 million years ago. The continents gradually fused to form Pangaea, a single supercontinent surrounded by a global ocean. This configuration drastically reduced humid coastal zones. The continental interior became dry, hot, and hostile. Forests retreated. Deserts expanded. Life was forced to adapt to extreme conditions, marked by strong temperature fluctuations and water scarcity. It was in this context that reptiles, better adapted to arid environments, diversified. But these adaptations were not enough to avert catastrophe. Around 252 million years ago, the greatest mass extinction ever recorded occurred. It is estimated that more than 90% of marine species and nearly 70% of terrestrial species disappeared. Probable causes include colossal volcanic activity in Siberia, releasing immense quantities of carbon dioxide and methane. These gases intensified the greenhouse effect. The oceans warmed, became more acidic, and lost much of their oxygen. Coral reefs collapsed. Marine food chains were shattered. On land, vegetation withered, triggering the collapse of continental ecosystems. Earth came perilously close to a point of no return. Yet once again, life endured. At the dawn of the Triassic, survivors evolved in an impoverished world, dominated by desert landscapes and extreme climates. Biodiversity took millions of years to recover. The Triassic saw the emergence of new animal groups. including the first dinosaurs. Initially modest and inconspicuous, they occupied secondary ecological niches, but their efficient physiology gave them a decisive advantage. During the Jurassic, dinosaurs became dominant. Giant sauropods roamed the plains. Formidable predators ruled terrestrial ecosystems. The oceans were home to vast marine reptiles. The global climate was warmer than today. Forests extended into high latitudes. Yet despite this warmth, large regions remained arid. Earth was not a uniform jungle, but a complex mosaic of biomes. The Cretaceous continued this trajectory. The continents gradually fragmented. The oceans widened. Flowering plants appeared and diversified, transforming landscapes and food webs. Pollinating insects evolved in parallel. Ecosystems grew in complexity. Earth was drawing closer to its modern state. Then, around 66 million years ago, a sudden event brought the age of dinosaurs to an end. An asteroid several kilometers in diameter struck what is now the Yucatan Peninsula. The impact released energy equivalent to billions of nuclear bombs. Fires engulfed the continents. Tsunamis swept across the oceans. Vast quantities of dust and aerosols were injected into the atmosphere, blocking sunlight for months, possibly years. Photosynthesis collapsed. Food chains fell apart. Non-avian dinosaurs vanished. Only a few lineages withstood the global collapse. From the ruins of that ancient world, a new era began. Mammals, long relegated to the background, were finally about to take center stage. After the Cretaceous extinction, Earth entered a new era, the Cenozoic. A world emptied of its reptilian giants, yet rich in evolutionary opportunities. Ecosystems, profoundly disrupted, gave way to a rapid diversification of mammals. Freed from the dominance of dinosaurs, these once discrete animals explored new territories. Some returned to the oceans, giving rise to cetaceans. Others took to the skies, becoming bats. On land, they diversified into massive herbivores, swift predators, and species adapted to cold, drought, or dense forests. The continents continued their slow drift. India collided with Asia, giving birth to the Himalayas. South America remained isolated for a long time, fostering a unique fauna. Antarctica, once green, gradually became covered in ice, altering ocean currents and the global climate. Over the last 60 million years, Earth slowly cooled. Polar ice caps expanded. Glacial cycles became more frequent. Landscapes alternated between temperate periods and harsh ice ages. It was within this changing context that the first hominins appeared. Bipedal primates capable of traveling long distances. Their brains, initially modest, gradually developed. Tools became extensions of the hand. Fire became a decisive conquest. Around 300,000 years ago, Homo sapiens emerged, a singular species capable of symbolic language, cultural transmission, and abstraction. For the first time, Earth produced a form of life capable of reflecting on its own origins. In just a few thousand years, humanity profoundly transformed the planet. Forests were cleared, rivers diverted, species domesticated. Fossil energy inherited from the Carboniferous was extracted and burned at an unprecedented rate. Never before had a single species altered planetary balances on such a scale. The climate warmed rapidly. The oceans acidified. A new mass extinction, this time of conscious biological origin, seemed to be taking shape. And yet, for the first time in Earth's history, a species was capable of understanding what it was doing, capable of observing past cycles, capable of anticipating, at least in part, the consequences of its actions. But the human gaze did not stop at the planet. By lifting its eyes to the sky, humanity began to question the universe. The first astronomical observations revealed that Earth was not the center of the cosmos. Then came the understanding of gravitation, galaxies, and the expansion of space. With the advent of modern telescopes, our perception changed radically. The universe revealed itself as vast, ancient, and in constant evolution. Each galaxy contained billions of stars. Each star could host planets. In the 21st century, the James Webb Space Telescope opened a new window onto the cosmos. It made it possible to observe the light of the first galaxies, emitted just a few 100 million years after the Big Bang. It revealed the atmospheric composition of distant planets. It offered clues about potentially habitable worlds. For the first time, humanity could detect the chemical building blocks of life beyond Earth. Water, carbon, complex organic molecules. In this vast cosmic ocean, our planet is only a fragile point. A living world born from chaos, shaped by billions of years of trials, failures, and rebirths. A world where matter became conscious of itself. The question is no longer only whether we are alone in the universe, but whether we are capable of preserving what allowed us to exist. For when we observe the stars, we are also contemplating our own future. In the silent immensity of the cosmos, Earth tells a rare story, that of a planet that learned how to live, and of a species that is only beginning to understand.